Hello and welcome back. Happy Friday, by the way. We made it to the weekend. So I know this has been a very long week for me. And I know some of the lectures that I made were pretty long for you as well. So luckily today, nothing really new. I'm just going to briefly repeat some of the stuff I talked about yesterday. So I'm going to get through this a lot quicker than yesterday's video. But make sure you watch yesterday's. That was 22-1. Gosset's t-distributions, because that's really the foundation of what we'll be doing for the rest of the year here. All right, so we talked about the fundamental theorem of statistics and the central limit theorem over and over again. What it tells us that is even when the population is skewed, unimodal, bimodal, multimodal, uniform, anything, anytime that the population distribution is not normally distributed like this one, we'll say that this is men's weight. So again, it's going to be skewed to the right, maybe not this much skewed, but I'm using the same graphic for everything. But anytime that the population is not nearly normal, it's okay, and we can still use a sampling distribution model and a normal model for that because it gets straightened out by the central limit theorem. Whenever we take means or medians or any statistic from a population that's not unimodal, those sample distributions, when we take the statistics from those samples, the sampling distribution becomes more nearly normal. So let's look at this example here. Now it is a modified version. It's the t-distribution, which are flatter and wider than the actual normal model. So Gosset discovered that with his drinks, right, from yesterday. All right, so let's say that the average American male weight is 190 pounds with some standard deviation. All right, so from that, we take a sample. It is a skewed distribution because you can't get much smaller than 130 pounds as a fully grown adult. But you can always get bigger. Think like my 600-pound life, right? So there are some people that are really, really heavy. Used to watch Biggest Loser with my mom all the time. Anyway, so yeah, people can get really big, especially Americans, right? So on this one, 190 pounds, that's the mean, that's the average. And keep in mind that average is being skewed to the right because the whole distribution is skewed to the right. All right. So if we take a few samples, so these are 3 different samples. Let's say there's samples of 10 American male adults, just like our example with the elevator. So one sample here has one of those outliers. So say this person is 400 pounds or something like that. So not the extreme outliers, but still 400 pounds would be an outlier. Well, what happened to the sample mean? So if this was the only 10 Americans that we knew, we would infer that the actual average American male weight would be 200 pounds. But partially that would be because of this skewed data here. All right, so if we took another sample of another 10 Americans, notice how these bins are not as wide, they're wider, so they're not as narrow. That means that this one's not as much of an outlier. So maybe that was like 300 pounds. So here's a 300-pound American male. Well, that was a bit of an outlier, but not as much as what we would expect because we only had one person. Maybe the next biggest person was like 250 pounds or 220. So it wasn't as skewed as the population. And so instead of having a population, well, the population mean is 190, but this had a sample mean of 180. So it was less than the population's mean. Then over here, we don't have really any outliers. We have a lot of really small people, maybe around 150 pounds or something like that. So really lightweight people. Well, I guess it'd be 160 pounds, right? And so that caused us to have a smaller mean than the population's mean of 190 of about 170. Now, when we take those samples, those means, and we put them all together, that will give us a sampling distribution. And the model that we would use for sampling distribution is actually a T model given on our degrees of freedom. So the reason why we don't use the normal model, which is the blue one here, the reason we don't use the normal model, and before Gosset discovered the whole problem with Guinness, the reason we don't do that is because when we take the sample means and we take the standard deviation of our sample, the standard deviation is always going to be less than what it would be if we were comparing it to the actual true mean of 190. So when we take the standard deviation for this sample, and it's how far is this value deviating from 200, and then we square that, right? We add the sums of those deviations. Well, we actually should be taking those deviations from the true proportion mean, or sorry, not true proportion. I'm still stuck in last unit, but the true mean of 190. But the problem is we're trying to estimate the 190. We don't know what that is. Our best guess is the 200, which is from our sample. But again, we don't know what the 190 is, so there's no way that we can actually compare, and that's the whole point of inferential statistics. We're trying to find out the population parameters, or create a confidence interval to try to figure out where those might be based on our sample. So the problem is that we actually have more variation in the true amounts than we do in the sample and what the sample is going to represent, because the actual values of our sample are always going to be closer to the mean of the sample than the actual population. Same thing here. The deviations that we would measure from the mean of the sample mean of the Y2 bar right here is always going to be less variation than what it would be if we measured it to the 190. But again, we don't know what the 190 is. And the same thing here. These values are all going to be much closer to their average than the population's average. So the sample average and the population average. All right, so what happens? Well, when we put those together, it's going to give us a smaller amount of deviation or variation from the means, their individual sample means, than there actually should be. So what results is that in order to correct it, we basically end up dividing by n minus 1 instead of dividing by n. And that's because our standard deviation comes from a sample and not from the population itself. And that is actually fixed by using a different model. Instead of using a normal model, we'll use the students' T models, which are it's just the whole family of normal models parameterized by the degrees of freedom. And the degrees of freedom is always one less than the sample size, because we have it's the number of parameters that we're estimating is always, and there's one of them that we are, so it's one less than that. So especially when we have small samples, it's going to be quite a big difference than the normal model. And that's what Gossett discovered, because he was only allowed to take samples of 3 glasses a day, because he wasn't allowed to drink more than that for his health and productivity. All right, so this is a very, very important slide. If you can understand what's going on here, I can't think of any better way to visualize the whole process and why we have the issues than this one slide. So I know I spent 8 minutes talking on one slide, but it's worth it. All right, so when we create our confidence intervals, this is when we create our confidence intervals, it starts with our sample, whatever our average was. So let's say that was like the 200. So we'd start at 200 plus or minus some critical value times the standard error. So the critical value just tells us how many standard errors we go over, and altogether the critical value times the standard error is the margin of error. So the plus or minus part in our confidence interval. Now, this critical value used to be called a z-star, right? And these are the ones that we use for the normal model found from the inverse normal. It's the area, it's how far we have to go out to, how many standard deviations we have to go from the mean in order to have 90% of the area in between it from the center, or 95 or 99%. But the problem is when we want 95%, when we have infinite degrees of freedom and it's a normal model, then that's 1.96. That's fine. But if we have a sample of 7, so we have 6 degrees of freedom, now we have to go 2.54 standard deviations out. So it increases the width of our confidence interval, because in order to have 95% of the area in the middle, we have to go further out in order to only have 2.5 on each tail. All right, same thing if we have a really small sample, and this is Gossett's, right? So he had a sample of 4, so 3 degrees of freedom. It's really flat here, and that's why he had 3 times the amount of false positives, because he was using the normal one instead of going all the way out here. And he should have gone 3.18 standard deviations and not considered it unusual or rejected the null hypothesis unless he was 3.18 standard deviations above the mean instead of being 1.96. And we talked about how he, I think he gathered data from like 10,000 or something like that prisoners of their heights, and he stimulated the process, and he actually came up with this model here based on his results. But the problem is that there's infinitely many models, and I showed you that from GeoGebra yesterday as well. So we really couldn't go through that whole process he did over and over again for each one. That would be so annoying. So they had to figure it out mathematically, and they did that many years later. I think it was Fisher who did it. All right, so students' t distribution. So we're on the homework. That was it. So 10 minutes in, and then we're straight to the homework. So a student's t distribution is a family of distributions. So it's a family of models, like the normal model, but they're all going to be a little bit flatter. The most extreme, of course, is when we have sample sizes of 2 or 3 or 4. This is sample size of 4. We really can't have a sample size of 1 because that's just the population itself, and that doesn't really help. So family distribution of models indexed or parameterized by its degree of freedom. So that's how we call it. So this is T's model with degrees of freedom of 6. Usually we put T sub 6. T models are unimodal and symmetric, bell-shaped, just like a normal curve, but are generally have flatter tails and a narrower center than the normal model. As the degrees of freedom increase, the t distributions approach the normal model. So as we increase the sample size, really anything above 30, it's pretty close to an actual normal model, but we always use, even with samples higher than 30, we always use the appropriate t distribution because our calculator is doing all the work for us anyway. All right, so one sample t interval for the mean. So a confidence interval is centered at our sample mean plus or minus the t critical value. Now this is not the z star, the critical values. This is now a t star, and that's parameterized by whatever that value comes from the calculator when we use the inverse t function for like 90% confidence, 99% or 95% or something like that. So we have to look this up in the calculator. There's no reason to really memorize those. Kind of like when we memorize all these values, the values change for every single model. See that? See, these are all 95. They all change for whatever that number is. So just look it up in the calculator. So you need to know how to put it in the calculator is what I'm trying to say. All right. We talked about that one. All right. With the standard deviation or standard error, because it's from the sample, is the standard deviation of the sample divided by the square root of n. All right, so when we use the t star, that tells us how many standard deviations we have to go out. And again, we have to look that value up. So we don't go out 1.96. It's probably going to be more than that, especially unless we have a really, really, really large sample. That and as it goes to infinity, of course, it does approach a normal model. But anyway, look up that value and tell you how wide you have to go out. All right, one sample t-test. So we're doing hypothesis testing again. That hasn't gone away, but now we're doing testing for means. So we want to we'll have some null hypothesis that, like the null here is that the mean is equal to mu naught. So we'll say we're going to hypothesize that the average American male weight is still 190 pounds. And then we take a sample of 10, and if our sample mean was was an observation that was statistically significantly far away from what our null hypothesis was. Say we had an average of 10 that had a sample mean of like 250 pounds. That might be statistically significant enough for us to say that we believe that the null hypothesis is not true and that we can reject it for the alternative, say a one-sided test saying that the average American male weight has increased. All right, so one sample t-test for the mean, test the hypothesis for some mean using the statistic. All right, so we use a t-score instead of a z-score. We use z-scores with proportions because we were using a normal model, which is z-scores, right? But we're using t-scores. It's just telling us that it's from student's model and that it's from a different family of models here, okay? So we would have gone 1.96 if it was a normal model with an infinite degrees of freedom, okay? It does approach that when we're doing means. Degrees of freedom of 6 would be going 2.54 standard deviations out. And then Goss's experiment, he should have gone 3.18, and this would be 5% under the curve when he thought it was actually here would be 5%. That would, under this curve here, that is 5%, but he would have had to gone further out to only have 5% false positives. All right, so we're on the assignment number 8. Teachers, a software analysis from salaries of random sample of 288 Nevada teachers produced the confidence interval shown below. So the T interval value for mu with 90% confidence, we believe it's between 38.9, that number, and the average teacher pay. So make sure we're reading this right. We're not talking about an individual. We're talking about the overall average teacher pay for Nevada teachers. And we're not extrapolating out to other states or anything like that because and depending on cost of living, they're going to pay teachers differently. So like teachers in California, I believe, get like they start out like $80,000, but cost of living is so expensive that's not that much to live on. All right, so we are 90% confident that the true average teacher pay for Nevada teachers is anywhere between this number and this number. Carefully explain what the software output means. Okay, so again, we're 90% confident that the true average teacher pay for Nevada teachers is between this value and this value. What's the margin of error for the interval? So to find the margin of error, all we have to do is subtract. So we're going to take, 42,893. Why am I typing it in like that? Okay, so that minus 38,944. Okay, so that's going to be the plus or minus, which is like twice the margin of error because we're going from the far left to the far right. So all we have to do to find the margin of error is we divide that by 2, which will give us a margin of error of that. So if we took our average, which if we take that value and we add it to the bottom one, all right, so what we could have said was that we believe that you could also write your confidence interval a different way is what I'm trying to show you. Ready? So let me scoot this over. There we go. How nice. All right, so we can say that we believe that the average was $40,918.5 plus or minus our margin of error, which was $1,974.5. Okay, so that's the basic math. If you understand how it works, you can do that. But lots of times they'll give us this, and sometimes they're going to ask us what the margin of error is for the interval. All right, we'll go back to where we were. Okay. So 42, was that it? Or was just part B, A and B? Let me see. Yeah, just A and B. Okay, 42. Yogurt. Consumer Reports tested 14 brands of yogurt. Actually, I'm going to go back to here so I can show both of them. Tested 14 brands of yogurt and found these numbers of calories per serving. All right, so we have all that data, which is kind of cool because we actually get to put this in the calculator. So make sure you have your calculator. Check the assumptions and conditions for inference. Be sure to plot your data in the histogram. So randomization condition, 10% condition, and nearly normal condition. Okay. All right, so let's put this into the calculator. To do that, we go to Stat, Edit, which will go to our list menu. And I've already put all of them in there. There's just 14, so it won't take you too long. So when we get done, it'll say list 1 and 15, because that's the last one, would be in the 14. All right, so what we want to do is we want to make sure that we believe that the population is nearly normal. So our sample size is only 14. So the central limit theorem is going to kick in with that large of a sample. This is kind of a moderately sized sample for means. And so as long as the data is not, as long as we don't believe the population to be super skewed to the right, maybe like children's yogurt or something like that, like cereal is going to be, there's going to be some far outliers. But even if there are outliers and it's skewed to the right, the central limit theorem is going to kick in with a larger sample, like 14, and we'll still be able to use all of our inferential models. Okay, so that's this nearly normal condition here. So again, we're going to go ahead and graph this out. So I guess I'll go ahead and get to it. So we'll go to, second, y equals stat plot. We'll turn the first one on. We're going to go over to a histogram, which is the third option. And this is from list 1, frequency is 1. And then we go to zoom and 9, and that'll do zoom stat. All right, so our sample looks nearly normal. And remember, samples are going to vary from sample to sample, just like we showed at the very beginning, right? These are all samples varying from sample to sample. Now, these samples are representations of the population. So when we look at this is not the population, right? This is a sample. So kind of see where we're at in the whole process. And what we need to make sure is that our sample's large enough that the sampling distribution model will become nearly normal, even though the population is slightly skewed, right? So that's really the question we're asking. And so if I get a sample that looks like this one, is with sample size of 14, that's going to be large enough even if it is skewed. But our sample isn't showing that. It looks pretty much like a bell curve, right? Which tells us that we think that our population is really close to a normal model, and especially with a sample size of 14, we're definitely good to go. So some good thinking going on right there. All right, so nearly normal condition. I know I skipped these two, but we'll go right back to it. So the question is, from our sample and with the sample size, do we believe that our population is normal enough? Or if it is skewed, is our sample size large enough that the central limit theorem kicks in and allows us to use a bell curve, or students' t-distributions in inferential statistics? Anyway, so yes, we believe that from our sample it's nearly normal, meaning we believe the population is normal, and with this large enough sample, we should be good to go. All right, so let's go back over randomization and 10% condition. So is this a random sample? So they took 14 brands of vanilla yogurt. Was this a random sample of all the vanilla yogurt? No. So we want to be careful when it's not necessarily a random sample, like a simple random sample. We took a list of all the brands of yogurt, and then we took a simple random sample, assigned numbers of 14 and picked 14 of them brands, right? So it's not a simple random sample. The question we would want to know is, do we still think that it's representative of all the vanilla yogurt that's out there? So we want to know where they get this stuff. So did they go to like a health food store? Did they only pick children's, yogurts that's branded towards children, or what's going on here? So as long as we believe that this is a representative sample of all the yogurt out there, it's okay that it's not a random sample. All right, 10% condition. So this has to do with independence. So when we're sampling, we're not sampling with replacement. We're not going to allow us to pick the same brand twice, even though here it looks like we had the same number twice. We're going to assume those are different brands, but because we're not sampling with replacement. When we sample one of them, it does change the probability after that. So they're not truly independent, but as long as we sample less than 10%, we can override the independence assumption with a 10% condition. So the question is 14 brands of yogurt, is that less than 10% of all brands of yogurt? Yes, probably. There's probably more than 140 brands of yogurt that are being sold. All right, so there's our assumptions and conditions, so we're good to go. Create a 95% confidence interval for the average calorie content of vanilla yogurt. So we have the data in here, and the calculator is going to do it for us. So we go to stat test, and we're going to create a confidence interval. So we're looking not for a test, we're looking for an interval. The first interval we want to see is a z-interval. Now, if we try that one out, data, what does the sigma stand for? So we're looking at the sigma of x or the s of x, the standard deviation of x, or of the standard deviation from a sample, or standard deviation of a population. Now, the z-interval is using z instead of a t, which tells us that it's using the normal model instead of Gosset's models. Do you see any degrees of freedom here or sample size? No. So this would be okay if we knew the true population parameter. But again, we never know, or most of the time, we don't know the true population parameter. So if we knew we were comparing this to 190, because that's what the actual true value was or whatever, that's the mean, this is standard deviation. But if we knew the population's parameters, which we don't, then we could use a z-interval. So instead, we want to go to a t-interval. And the t tells us it's Gosset's distribution when we're dealing with means. All right, cool. So data's here. And it knows it's a sample, so it's not even going to ask us about degrees of freedom or anything, because it also knows the sample size from the list size from the data. So it's just list 1, frequency 1. If you're putting it in like a relative frequency table, so like your values are in one list and then the frequency for those values is a second list, then you would put like list 2 there, or whatever that frequency list is in. Confidence interval, we wanted, I think, 95%. Let me go back to where we were. We wanted, 95% confidence, and hit calculate, and it does all the work for us. Now, getting the answer and interpreting the answer are two different things. So Just because you can write that down, yes, I would give you credit on the test, but we need to be able to interpret it and interpret it correctly. So Diet Guide claims that you'll get 120 calories from a serving of vanilla yogurt. So if you tell them you ate vanilla yogurt, they're going to count that in your calorie log as 120 calories. So what does the evidence indicate? So remember, in our confidence interval, let's go ahead and interpret it. We're 95% confident that the true average vanilla yogurt calorie content is in between 132 and 183. Now remember, we are estimating what the mean is for the population, which is all vanilla yogurts. So we believe that the average vanilla yogurt, not the one that you chose, not any individual one from a sample or a sample average or anything, we're just looking at finding the population parameter for the average yogurt content. So we believe that the true average is in between 132 and 183. Now they claim that's 120. So comparing that to our 95% confidence interval, which could be wrong, right? 5% of confidence intervals would fail to capture the true population mean. Could that be this one? I don't know. But based on our interval, we're going to have to reject this claim, right? So if our null hypothesis was that, so if we're testing, wow, I just totally confused myself. Anyway, so we would have enough evidence to reject the null hypothesis and to say that it's not 120. Yeah, that's our null. Sorry. If the null hypothesis was that it was 120, we would have enough evidence to say that it's not 120 with either 5 or 2.5% alpha level or significance level, depending if we were doing one-sided or two-sided. Okay, all that stuff is good stuff. Moving on. Also notice it gives you a standard deviation S of X because it knows it's a sample and the sample size, so 13 degrees of freedom, and it'll also tell you the average from our sample. Okay, I think that's it. All right, cool. So 26 minutes. I did a lot faster than we did yesterday, so sorry about that. I hope you guys have a good weekend. Enjoy your time off. If you're behind on any of the videos or the assignments, let's make sure we get caught up on that, especially if you're taking the AP test, because this unit is going to be on the AP test, and so we need to make sure that we understand it. So I'll see you guys on Monday, and enjoy your time off.